Georgia Tech is a winner. So today's speaker, it's a pleasure to have today's speaker, Professor Seth Marder. Seth got his bachelor's degree at MIT in chemistry and then his PhD at the University of Wisconsin, also in chemistry. Did a postdoc at Oxford before going to the jet propulsion lab at Caltech and a number of years at the University of Arizona before coming to Georgia Tech in 2003, where he is currently the Georgia Power Chair and Regents Professor in Chemistry and Biochemistry and also Material Science and Engineering. He's the Director for the Center for the Science and Technology of Advanced Materials Interfaces, also known as STAMI. And he has won a number of awards. He's a Fellow of the National Academy of Inventors, the American Physical Society, the Royal Society of Chemistry, the Materials Research Society, SPIE, OSA, and AAAS, to name a few acronyms. He's also last year's 2018 winner of Georgia Tech's highest honor for faculty, which is the Georgia Tech Class of 1934 Distinguished Professor Award. He has graduated over 250 students and postdocs and sits on editorial boards and conference chair positions. And so that's a real pleasure to have
Okay.
Thank
you. So it's a pleasure to be here. One of my guys pointed out to me that I'm giving a nano talk in the Petite building. And I guess people
it's actually the Pettit building.
So the other one's the Petite building?
The other one's the Petite building.
I'll never get that straight. That'll be my goal before retirement. So let me just tell you a little bit about myself. My background is actually originally as an inorganic chemist. And then over the years, I started doing more organic chemistry. And so how many people here are chemists? Okay. So the answer is not many. And so what I've decided to do is basically give you the bare minimum of chemistry, although the chemistry underpins everything that we do. Okay, so I've stripped out a tremendous amount of the hard work that our group has done to make new classes of molecules that hopefully do interesting things. I'll tell you a little bit about the strategy, but all the chemical stuff is going to be kind of just summarized in a couple of slides. And then the rest will be sort of show and tell. So you mentioned that I got the class of 1934 distinguished lecturer or distinguished professor award. When Charlie Leota got it, and I nominated him years ago, I referred to it as the class of 1934 extinguished professor, because basically that's something you get when you're really old. Okay. And I am getting there. I still have a few years to catch up to Charlie. I haven't made much progress on catching up to him yet, but it's been a long time since I've done a substantial amount of work in the lab itself. And what I want to do is note that none of the work here has been done by me, and that there are a lot of people in my group who have contributed to the design and synthesis of some of the materials that we're using, as well as the approaches that we've taken to understand how they work. And then we have long-standing collaborations, in particular with the Kipling group and the Breda group. I mean, Bernard I've been working with for 24 years, Jean-Luc for about 27 years. As well as more recent collaborations with Eric Vogel's group, Carlos Silva's group, Natalie Stingland's group, and Shannon Yee's group. And then what you can see is that our group has been pretty well integrated into groups all over the world. Okay, and so I think quite a few of the people mentioned here, you'll see work that was done in collaboration with these people. Okay, so I'm going to talk about a little bit about doping, and it's going to cover multiple topics. It's going to be covering doping at interfaces and also doping of organic electronic materials. And what you see here are pictured three guys, one of whom has passed away, Alan McDermott, a really nice guy from New Zealand, as well as Alan Heeger and Hideki Shirakawa. And these folks made the observation in the 70s that if you take a molecule, or an organic polymer actually, referred to as polyacetylene, which is just alternating in single bonds, and you treat it with iodine, the conductivity of that material goes up by something like 6 to 9 orders of magnitude. Okay? And so when we mostly think of organic materials, we think about them as plastics like this, as insulators. And today, they're being used as conductors. There was a report in Advanced Materials out this year of materials that, when doped, have conductivities of 10 to the 5 Siemens per centimeter. And that's with a group in Strasbourg with whom we're working on aligned polymers. And they're also used as semiconductors, okay? The most obvious case of these being used as semiconductors that you may be aware of one way or the other is in the case of cell phones, okay? So if you have an iPhone 10 or a Samsung phone or an Apple Watch, the display is made out of an OLED, an organic light emitting diode. My TV at home is an LG 65-inch TV, and it's made out of an OLED display. It looks gorgeous. Other applications that people are playing with pertain to photovoltaics. A few years ago, the maximum efficiency of a photovoltaic system was on the order of 7% conversion efficiency. Now there are single junction solar cells based on purely organic materials, except for the electrodes, that are around 18% efficient. If you had asked me 7 years ago, would that be possible, myself and my colleagues like Bernard Kippelin would have we would have laughed. Okay, so these things are coming along. People are doing printed electronics. People are doing bioelectronics using these. And so it turns out that like other semiconductors, and I'll go into this in a little more detail, that you can dope them. But the whole concept of doping in organic semiconductors is somewhat different than inorganic materials. And that when you dope them, you can increase their conductivity by injecting carriers. You can inject both electrons and holes. You can fill traps that improve the mobility. You can also have doping near interfaces with electrodes that can lead to either more efficient charge injection into the material or charge collection from the material if it's a solar cell. And I have a couple of bullets for how that's done. And as I said, these have found applications in OLEDs, OPVs, OPETs, and other applications. I just got a manuscript to work on today, some colleagues in Singapore who have been basically using doping to enhance the photo sensitivity of black phosphorus layers. Okay? So Shirakawa, Alan McDermott, and Alan Heeger shared the 2000 Nobel Prize for the realization that you can dope organic materials and make them highly conductive. And then it was later in the 80s that people really began to focus on the semiconducting properties of materials. Ching Tang, who was at Kodak, made the first observation of two things. One is systems that had, quote, reasonable efficiency as an organic light emitting diode. They were getting like 1%. And also the efficiency as solar cells, where they were getting 1%. And that has blossomed between 1986 and his reports in Applied Physics Letters, okay, to OLEDs being a multi-billion-dollar a year market, and OPVs going from something that was not even conceivable to something that might be conceivable for consumer electronics applications, or but not likely for large area applications. Okay? So organic materials are somewhat different than inorganic materials, and I'll just talk about that in a second. First of all, crystalline inorganic materials, and probably the vast majority of people here who work in electronics work with crystalline inorganic materials, have a really well-defined lattice, and that they'll have a dopant atom that has either one fewer or one greater electron than the host, okay, which leads to the system being either p-doped or n-doped, and leading it to be a hole or electron transport material. Organic materials, by comparison, are a complete mess, okay? If you look at the best crystalline organic materials, an inorganic semiconductor person would look at them as highly disordered, impure materials. And we don't typically use highly crystalline materials. We use amorphous materials and we use polymeric materials. Okay? And amorphous materials, polymeric materials can be amorphous, but we can also use small molecules, okay, that can be evaporated and make amorphous glassy films. And then we can have impurities, which are dopants. And in the context of organic molecules, doping is somewhat different in that it involves an oxidation reduction process, and I'll show that more on the oncoming slides. And the way we think about the transport of materials in an organic system is somewhat different. In inorganic materials, we think about the conduction through valence bands and conduction bands. And in organic materials, people somehow use that language, but maybe not in the same way that people in inorganic community use them. In particular, what we have is a manifold of localized transport states on either individual molecules or on segments of a polymer, and that we can have gap states, as you can in an inorganic material, and that when we dope, what we do is we take one electron out of a molecule that is in the whole manifold of states, and we can call that, p-doping. And when we n-dope, we put an electron in here. And we typically don't see band-like transport. We see a thermally activated hopping transport. We're working towards seeing more band-like transport. And in fact, I'm part of an NSF team of people working to do that. Okay, so that's a bit of the differences. So when we look at doping of materials, we could talk about n-dopant. And what we have is a dopant, okay, and a host. And what happens when we dope is that the dopant transfers an electron to the host, the dopant becomes oxidized, the host becomes reduced, okay? Or we can p-dope. And in that case, what we have is a material where the dopant becomes reduced and the host becomes oxidized. And so this would be a hole carrier, this would be an electron carrier. Now the requirements for these dopants are that they can have we would think, but it's not exactly true, that they can thermodynamically accept an electron from the host if you have p-doping, or donate an electron to the host for n-doping. I'll show you a system where there's an exception to that, which might be interesting. But fundamentally, if we want the dopant to transfer an electron to the host, we can basically ask for a system where the ionization energy of the dopant is less than the electron affinity of the host. Okay? And conversely, if we want to p-dope a system, we want the electron affinity of the dopant to be greater than the ionization energy of the host. Now, as I said before, it leads to all these different properties, which I mentioned. And here is a little zoo of molecules that have been N and P doped. Okay? And probably for many of you, this just looks like chicken wire. But we basically can look at these molecules and think about how we design them and how their detailed chemical structure will actually pertain to their color, their emissivity, their electron affinity, their ionization potential, whether they form crystalline materials, whether they form glasses. Okay? And this is the hype or the sales pitch that we often give, is that these materials are extremely tunable at the molecular level in such a way that from their molecular constituent properties, we can have a guess at many of their bulk properties. Okay. So what, if you are going to be a chemist working on doping, would you do? How would you contribute to this field that has been largely dominated by physicist electrical engineers? Okay? Well, what we can do is expand the palette of dopants and make things available to people that have some unique sets of properties that they can use. And so what do you want as a dopant? Well, what we want is complete and clean electron transfer from the dopant to the host, or vice versa. We want, therefore, the ionization energy of the host to be as low as possible if we want to dope something that has a very low electron affinity, okay? Or we want the electron affinity of the dopant to be as high as possible if we want to take an electron from something that's very hard to oxidize, okay? We don't want the dopants themselves, the molecules, to have side reactions. We don't want the ions that we create, once we dope, to do side reactions, okay? We may want to, if we have a multi-layer device, be able to spatially localize these materials in the layer that we want. We may want these things not to act as traps, although you can imagine situations where you want to control the number of traps. And we'd like to be able to deposit them both from solution and from vacuum. And ideally, we'd like to handle these materials in air, okay? So for p-dopants, things that are oxidants, in general, except for the most oxidizing of materials, that's relatively straightforward. Some materials will actually interact with the water in air and become reduced, and that can be problematic. For n-dopants, it turns out that that's a much more challenging situation. Because if you look at the materials that you want to dope, typically it will require something to dope them with a sufficiently low ionization energy that oxygen can oxidize the dopant, okay? And we set out for ourselves the challenge of identifying dopants that would be relatively stable in air and yet be able to dope things that are very, very difficult to dope, i.e. have very low electron affinities, okay? So I'll just mention that there are a whole slew of different kinds of p-dopants that we've worked with over the years, some of which were developed in our group, others in other groups, okay? And these are materials that have relatively high electron affinities. Electron affinities on the order of, in the case of some of these, around 5.4, okay, electron volts, okay? For n-doping, a lot of work has been done with alkali metals. That's not surprising. They're very highly reducing. They can be evaporated. They are often mobile ions after they transfer the electron, which can be problematically. They can also act electrostatically as traps, and they're going to be pretty air sensitive. So let me give you an idea about that, okay? So here we consider a reaction, and I'm going to be focusing today on n-doping, okay? And the reason I'm going to be focusing on n-doping is that developing air-stable n-dopants is much more challenging than p-dopants, okay? So here what we have is a donor, that is the n-dopant, an acceptor, that is the host, okay? And we do an electron transfer reaction. So if you look at the kind of materials that we might examine which simply give up an electron, in much the way that sodium gives up an electron to become a sodium ion, there's a molecule called cobaltocene. It's a well-known molecule. It's been synthesized probably around when I was born, if not earlier, okay? And it has around the metal 19 electrons. What that means is that there's one electron that's in a very high-lying antibonding orbital, and the molecule wants to do whatever it can to get rid of it. And so it'll donate it to something else. Okay? So if you look at the oxidation potential, or the couple for cobaltocene and its cation called cobaltocinium, it occurs at about negative 1.3 volts versus ferrocene. Okay? Now that's fine to dope something which would be an acceptor in a photovoltaic system and maybe a transistor, okay? But it would not even come close to touching something that you would want to dope for an organic light-emitting diode. And then we can go and make compounds that are even more reducing. We can decorate the rings with methyl groups. We can make compounds like this, compounds like this. And now this guy is already quite air sensitive, and these guys, you can't even touch them in air, okay? And this is where we need to be for OLEDs. So then the question is, how do we get around that? And the idea that we had, and it's shown schematically here, but I'll show you examples on further slides, is can we have a system where we have something that is very reactive and wants to give an electron, which itself has an odd number of electrons, and then when it gives an electron, it makes a stable cation. And can we have that odd number of electron masked when we use it as a bond? So two electrons on two of these things come together to make a dimer. And so we have a situation where instead of having one thing that's highly reactive with this electron it wants to give up, we form a bond. But we don't want that bond to be so stable that it loses all the reducing force. Okay? And so then the idea is that we have that dimer. It can react with two of these acceptors to give two cations and two anions. Okay? And so what we are doing is we're kinetically stabilizing the dopant at the cost of also thermodynamically weakening it a bit. But we might be able to make it air sensitive. Okay? And so our initial idea was to basically have a system where we can take the dimer and using heat or light, we can just cleave the dimer into two things. Just homolytically break the bond and then generate the reactive species, and then it will dope. So one manifestation is shown here. Here's a radical which doesn't exist for any appreciable time, okay? And this radical can go away and leave a positive charge, and you'll see this later, okay? But if two of these come together, we can form a bond, okay? And the idea was to do that and then be able to somehow cleave that bond and access the dopants. Well, my background, as I mentioned earlier, was inorganic chemistry, and in particular, inorganic chemistry that involved the combination of inorganic and organic ligands, which is known as organometallic chemistry. And what we knew is that there are molecules like cobaltocene, which I showed you a couple of slides earlier, that have 19 electrons, but they will actually react with each other in the manner that I had just mentioned to make dimers. And that one classic example of that is a dimer that's based on a rhodium, and that rhodium is the element that's just under cobalt in the periodic table. And what was also known is that you could heat this material, okay, the dimer of this material, and on a cold finger at 77 degrees Kelvin, you can basically isolate the 19 electron compound, which is highly reducing, but if you warm it up, it will dimerize again. Okay? So there are a series of these things, some based on the elements of rhodium and iridium, some based on iron and ruthenium, and there are even some that are based on osmium. Okay? And then we discovered something actually by reading the literature on some of these compounds. And that was, which was not surprising, that if you take a cation of a rhodium compound and you reduce it, and then you look at, in an electrochemical cell, the reverse wave, you can see there's more current here than there is there. Okay, which means that when we reduce this to the 19 electron compound, it's actually going away before we can reoxidize it. And then when we look back, we can see there's a blip over here. And that blip over here is due to the dimer of that compound. Okay? Now, the other thing which we noted and we had not really considered is that if you start with the dimer and now you go and you oxidize it, okay, and this is just a standard, internal standard. When you come back, you don't see the reverse wave of the cation of the dimer. What happens is once you take one electron out of this thing, it falls apart. And you get one equivalent of a cation and one equivalent of a very, very reducing material that itself, okay, is very quickly oxidized. Now, you might get some insight into this by looking at the crystal structures which we have. And what I'll point out is that the bond lengths, the single bond lengths in these molecules are very, very long for normal organic molecules. A normal organic molecule will have a bond length of about 1.46 angstroms, okay? And these are almost a tenth of an angstrom longer. And that may be associated with the fact that the bond is weaker. The other thing that you can do is look at the molecular orbitals. Okay, and the highest occupied molecular orbital has character in that single bond. In most molecules, that bond is, the single bonds are much, much lower in energy for the filled orbitals than the double bonds or the metal orbitals. Okay, so that's also unusual. So what that showed us is that potentially these class of dimers can react by two different mechanisms. One is the one that we first thought of, where the dimer cleaves and then gives two very reactive materials that transfer electrons. The second one is where the dimer, okay, as was the case in the electrochemical experiment, goes and in a process that may be uphill, transfers one electron to a host. And then you make the cation radical of that dimer, and then as I said before, that immediately falls apart to give you a cation and an anion, and now you have that highly reactive odd electron species, which immediately finds another acceptor, and then you get two of these cations and two anions. So what I will tell you is that our initial intent was to do this, and the vast majority of the things that we have ended up making go by the second mechanism. And I will not bore you with about 2 man-years of work at least of how we went and figured this out. But I can tell you that the kinetics of those two mechanisms are very different. Okay? They have different rate laws. One will involve things where they can come apart and come back together, and we can do experiments with isotopic labeling to look for that. We can see whether the first step has a dependence on the redox potential difference between the donor and the acceptor, which is indicative of the second mechanism, and we can look at things like the entropy of activation. And with all of that, we figured out how these worked, and then that gave us insight in how to go and design new materials. Okay? So that's basically it for the chemistry, more or less. So now what I'm going to do is just a little show and tell about some of the applications. This is a small list. These things are now being used by, I don't know, 20, 30 groups around the world to do various different things, and I'll just walk you through a few. The idea being to give you an idea of what could be done so that it may stimulate you to think of applications. Okay? So if you have a material that is made up of organics, because the materials are amorphous and inhomogeneous, okay, the LUMOs, the unoccupied states, are not all at one level. Okay, they're all in slightly different environments, and that leads to them occurring at slightly different levels. Okay, and so what you have is a distribution of energies to reduce them. And it may be relatively narrow, but then you can have outliers, okay? And those can either be to impurities in the system, they can be to very odd configurations of the molecule in the system. And in those cases, for example, these empty orbitals may be much lower. So if you're an electron that's sort of hopping along from here to here to here to here, and then you get down there, to get back up into this manifold is going to require energy. It's going to slow down the electron. But what if we could fill these low-lying states with electrons? Then we would only have to have the electron go from here to here to here to here, and the mobility would be higher. So you can do that, and the way we've done that is by having one of our dopants that's a strong reducing agent, and by just putting in tiny, tiny amounts of it, such that there's only enough of the dopant in the system to fill the trap states, but not enough to go and start filling this actual manifold of transport states. Okay? And when you do that, the example that this was done on was C60, and the dimer was one of these dimers based on a ruthenium cation. What you can do is if you heavily dope, you can just reduce and make the ruthenium anion. Okay? But if you very lightly dope, then you'll just fill the trap states. And in fact, what you see is that when you look at the work function of the material and the HOMO position, you'll see that there are two regions for the work function and the HOMO position. One which has a steep slope and one which has a narrow slope. So what's happening is that in both cases, okay, what's going on is that in this low doping region, we're filling the trap states. There are very few of those trap states, so a very small number of electrons is going to lead to a large change in work function. But then when we actually begin to fill the manifold of the states that are where we're really reducing the molecule, okay, then it takes many more electrons to lead to a change in the work function, okay, and that's what we see here. So one of the things that you can do is ask yourself, what kind of effect does that have on an organic field effect transistor? And one effect that it has on is in the threshold energy that is required to turn on and off a transistor. And this is work that was done in collaboration with Antoine Kahn and Bernard Kiplin. So you can buy C60 from Aldrich, and it comes as 99.9% pure. Okay? And if you make a transistor out of it, it has a turn-on voltage of about 18 volts. Okay? Now, if you go and you purify it 5 times by taking the pure C60 that you get and sublime it 5 times, that drops down to about 6 volts. If you now take that material and add 10 to the minus 3 mole percent of dopant, okay, what happens is the threshold voltage drops down to 6 volts, which is equivalent, without any substantial change in the on-off ratio. So what we're doing is, before we even turn on the bias to get this thing to work as a transistor, we're filling the trap states, and then when we bias it, then we just immediately start dumping electrons into the transport levels. And so in this manner, we can take a material that was a little bit crappy, clean it up electronically, and have it behave better. Okay? Now, there are a couple of things that I want to mention to you. This paper was published in Phys Revlet a few years ago, and our collaborator in Princeton, Antoine Kahn, who's an electrical engineer, called this ultra-low doping. Now, for those of you who work in semiconductor world, okay, putting 10 to the minus 3 mole percent, you would consider either ultra-high doping, or you would even call it an alloy, okay? But in the organic world, you need to understand that when we dope things, we typically put in 1 to 10%, okay? So this is a cultural difference in what ultra-low doping means. The second thing is, you might say to me, as I have to many people, electronics is based on pure materials. Why would you take an impure material and then add yet another thing to it to get it to sort of behave like this, when you can just go and sublime it? Okay? I mean, silicon's sublimed a bunch of times. Why don't you just sublime it and get it really pure? And the answer is that an awful lot of the organic materials that are used, okay, are polymers. And you can't purify them that way. Okay? So you have to take what you're given and try to make the best of them. And this is a mechanism by which you may be able to take a material that doesn't have great electronic properties and improve them. Another thing that you can do is impact the levels that are required for injecting or collecting charges. Okay? So if you don't have your Fermi level aligned with the HOMO to inject the hole, you'll have a substantial barrier to inject the hole. But if you p-dope the material, what you can do, or the electrode itself as well, what you can do is shift the Fermi level relative to the HOMO and then lower that barrier. Okay? And so, and that can make injection a lot easier. So this is another collaborative effort between Bernard's group and ours, okay, where what was examined was C60 electrodes, and we had source and drain electrodes. And in one case, we had the source and drain electrode on top of the C60, and then on the other case, we put in 3 nanometers of, so there is something nano here, 3 nanometers, you'll see that a few times, of a dopant in here. And what happened was the measured OFET mobility, which is not an intrinsic material property, but it's a device characteristic from which people extract material properties, basically tripled. Okay? Why is that? Because here the current was not limited only by the resistance of the C60, but it was limited by the contact resistance at the electrode. And for many of you who might be thinking about working with graphene and other 2D materials, I have been told by the people who have worked on them that dealing with the issue of contact resistance is one of the challenges that you have to make good materials. So here, what happens is the contact resistance goes down by a factor of 2.5, okay? And therefore, the measured mobility gets closer to something that is representative of the intrinsic mobility. Here's another example that we did in collaboration with Mark Hersom, who is at Northwestern. Mark has done a lot of work on making electronics out of arrays of carbon nanotubes, okay? And typically, when you get carbon nanotubes, you end up making p-channel transistors. And we had the idea, and we talked to Mark at a meeting, and he said, yeah, let's try it, that if we just put a very, very, very light amount of dopant on there, such that we fill all the trap states in the gap, and we move the Fermi level near the conduction band rather than right near the valence band, could we convert these things from being p-channel transistors to n-channel transistors? And he tried different conditions, and you'll see here curves in purple, okay, green, and blue. And this is the on-off ratio, and the bottom line is that you can get good on-off ratios for n-channel transistors, okay, reasonable turn-on voltages, and here mobilities that are between 2 and 3 centimeters squared per volt second, which for organic materials, for an n-channel material, is not bad. Then a colleague, Jana Zumzal, has looked at another one of our dimeric dopants, this case based on an organic material, with somewhat different architecture and slightly different nanotubes. And what she's been able to do is, again, take p-channel transistors and dope them. And now what they're seeing are mobilities on the order of 10 to 15 centimeters squared per volt second. So what we've done is we've taken a perfectly good n-channel material, and we've used a trace, just a trace of dopant to change its characteristics. Getting a little closer to home, we collaborated with Eric Vogel and examined the doping of moly disulfide, moly diselenide, tungsten disulfide, and tungsten diselenide. And you'll see 2 slides on these materials, or at least one of them. Okay? And so with the n-dopants, we can basically dope the conduction band. With one of these dopants that we have, we can actually, in the case of tungsten diselenide, dope the valence band. And when you do that, you can dramatically shift the transistor characteristics of the dopant, of the transistor, okay? And you can tune that, okay? Now here's another example that was done by Wei Chen and his colleagues with our dopants in Singapore. And now, instead of, we did this in the case with Eric with solution processing, they vacuum deposited dopants on bilayers of these dichalcogenides. Okay, and here is the case with tungsten. Okay, and again, when they dope, they make these things pretty heavily n-channel doped. The conductance of the material goes up by 5 orders of magnitude. And the interesting thing is that when you expose this to either oxygen or air, even after 10 hours, basically you don't lose very much of the conductance. Okay. Another example, which is of maybe less interest to this audience, is that of n-doping a polymer. So there are many p-doped polymers, and the p-doped polymers, as I've noted, can give rise to conductivities quasi-routinely, okay, as high as 1,000 Siemens per centimeter, and in some recent cases, as high as 10 to the 5 Siemens per centimeter. For n-doped materials, if you get 10 to the minus 3 Siemens per centimeter, you're not surprised. You consider that okay. If you get 10 to the minus 1, you're feeling good. If you get 1 Siemens per centimeter, you're feeling very good. Okay? And so now with these dopants, what we can do is dope materials and get up to about 8 Siemens per centimeter, and also very high, or reasonably for endopolymers, power factors for thermoelectrics. What I hope to be able to talk about within a few months is a paper that we're working on now with this group in China, Jian Pei, who developed these polymers, where they're now seeing n-channel conductivities on the order of 90 Siemens per centimeter. And I'll just tell you that to our knowledge, for a solution process material, 8 Siemens per centimeter is unprecedented, and 90 Siemens per centimeter, people might have raised their eyebrows as to whether you could do. Another example of this is the use of these dopants to make electron extraction layers in vacuum deposited perovskite solar cells. And this is work done in collaboration with Henk Bolling at the University of Valencia. So they have a system where they basically deposit ITO, then they dope a very thin layer of C60 with our ruthenium compound to make an ohmic contact. Then they have a little buffer layer of C60. Then they have the perovskite. Then they have a hole transport material, a doped hole transport material to make an ohmic contact, okay, with the hole conducting layer. And what I can say is that in the absence of the dopants, you get these odd-shaped curves. We're calling them S-shaped curves in the community, and that is indicative of a barrier to get the electrons out of the device. You put in just a tiny, tiny bit of, well, actually it's about 6 weight percent of this into this material. And you see here the curves, which are classic curves for a PV system. Okay, so we've basically killed the charge barrier for collection of the electrons. And one of the things that's also important in the world of perovskites is something called hysteresis, and that is when you look at the scan going up in potential, and then you look at the scan going down in potential, they're different. Okay, and here what you are looking at is the scan going up and down in potential. Okay, here you can see the hysteresis in the blue curve, one that goes up, one that comes down. Okay, actually it's probably one that goes up and the other one comes down. Here they're superimposable, which means that the issue of hysteresis is not something to worry about. You can use these dopants to modify the work function of materials. Okay, so let's assume you have something like indium tin oxide that has a work function. And then we react it with something that is a strong n-dopant. At the interface, what we can do is dump electrons into the ITO. When we do that, we oxidize the material, and then what we end up putting is cations right on the surface. Okay? And what that does is it creates something that's called an interface dipole that shifts the vacuum level, okay? And as a consequence, okay, the work function goes down. So let's see what you can do with this. And we'll show a few examples. Okay, so here are a bunch of different materials, ITO, dirty gold, dirty silver, P-PSS, which is an organic material, clean gold, moly oxide. And here are all their work functions in the absence of doping. And then we put down literally a nanometer or so of dopant on top. By and large, a monolayer. Okay? And now what you can see is that all these work functions get below 3. So we've taken materials that would normally be good anodes and we've turned them into cathodic materials. Okay? And then you expose them to air. Okay? And you can see that there is some loss of that decrease in work function, but it stays pretty constant. Okay? And the point being that we can make low work function materials that are by and large air stable without having to use things like calcium. A very extreme example of that is shown here. Okay? This is actually single crystal zinc oxide that was grown, okay, in UHV. And when you expose this one to on the order of 5 angstroms, a half a nanometer of this ruthenium acetylene compound, the work function drops from 3.7 eV to 2.2 eV. So as a reference, calcium has a work function of 2.8. So now what we've done, again, is we've made an extremely low work function electrode. Now there's another interesting thing here, and I won't go into all the details, okay? But what these folks were interested in doing was making a hybrid light-emitting device where they created an exciton in the zinc oxide. And then we're going to transfer that exciton to this material, which is highly, highly emissive. Okay? And they designed this material such that its HOMO-LUMO gap was just slightly smaller than the band gap of the zinc oxide. However, instead of getting a type 1 interface, they got a type 2 interface. And as a consequence, when they did the energy transfer, to this material to create a hole here and an electron there. They get a back electron transfer to the conduction band of the zinc oxide, which quenches the luminescence. When they put down a monolayer of this ruthenium compound in between, what it does is it creates just a touch of band bending. And it shifts those bands up such that now the conduction band is well aligned and the back electron transfer doesn't occur. And what you can see here in this inset is here is the photoluminescence in the absence of the dopant. And here is the photoluminescence with one monolayer of dopant. Okay? Now you could do the same thing with other materials. This is an example with graphene. We can p-dope graphene, okay, and we can n-dope graphene. When we n-dope graphene, we begin to fill the conduction band. When we p-dope, we get to deplete the conduction, the valence band. And we can modify the work function of graphene by, I show here 1.8 volts, but we can now modify it by well over 2 volts. And we can convert graphene into a very good cathode for injecting electrons into materials, for example, for organic light-emitting diodes. Okay, I have a couple more things I want to talk about, and this is a paper that was published, it's getting close to 2 years ago, in Nature Materials about doping materials for OLEDs. Okay, so when you want to dope materials for OLEDs, okay, it turns out that they have very, very low electron affinities. And as a consequence, it's very hard to dope them, okay? And so here is a material that's used in OLEDs. It's called POPY2. Its reduction potential versus ferrocene is negative 2 volts, okay? And its electron affinity is also 2.2 eV, okay? Now, it turns out that these dimers, if we broke this bond and made a radical, which we can't just cleanly, okay, would be plenty strong to dope this. If we have this, to transfer an electron here is very much uphill. But we can calculate through calculations and the experimental parameters that we have what the effective reducing strength of this dimer would be, which would be this reducing strength minus 1/2 of the energy required to break that bond. And the long story short is that we shouldn't be able to do this. It's uphill per electron 0.2 volts, and for the overall reaction of one of this plus two of these, uphill by 0.4 electron volts. Okay, so we shouldn't be able to do that, but we tried nonetheless. And the fact that we couldn't do it thermally because it was so uphill here, okay, we got around doing a technique that's called photoinduced electron transfer. And in that technique, what we do is we take this molecule, we photoexcite it. And what that does is it puts one electron from the HOMO into the LUMO in a very simple picture. And now this can dump an electron into the half-filled HOMO. And now we have it doped. As soon as we now have it doped, we make that cation. It falls apart, okay, to give one cation, one anion. And now we do have transiently this very reducing material which dopes another system. Okay? Now, here's a UV vis showing this, a ultraviolet visible spectrum. And this peak here is that anion growing in. We know it, okay? Trust me. Now, here's the interesting thing. I told you that that reaction was uphill by 0.4 of a volt. So we turn on the light, and it goes from a conductivity of 10 to the minus 9 or 10 to the minus 10 Siemens per centimeter up to a few by 10 to the minus 3. That's not that surprising with the light on. What was surprising is that when we turn the light off, okay, it stays for 100 hours. Okay? And in fact, we've now looked at this over 9,600 hours. Okay? And we only lose about 2 orders of magnitude of the 5 or 6 in conductivity after a year. So one of the things I joke with people about is that organic chemists look at photoinduced electron transfer in systems and photovoltaic systems and synthetic systems for looking at protein that do photosynthesis. And if they get charge separated states through photoinduced electron transfer that last microseconds, they considered that a long time. So I did a back of the envelope calculation, and it turns out that these things last 10 to the 13 microseconds. So from the standpoint of long-lived photoinduced electron transfer, these are pretty long-lived. Now, I will not get into a lot of the details, but what's interesting is that when you dope these materials, okay, the ability to inject charge in from the electrode becomes much, much easier, okay? And these things turn on, okay, very well, and they give very high quality OLEDs, okay? There's another story here, but I don't have time to talk about it, and that is that we can turn these things on electrically and not only using light, but that's another story. This slide I already showed. Finishing up, what we want to do for the community is give people dopants that have a variety of different doping strengths, okay, so that maybe we can dope everything, or maybe we can only fill trap levels, that we want to give them different shapes, okay, so that if they want something that's really large and doesn't move around, we have that. We also want to be able to control the kinetics. There may be cases where you want to mix things together, make a film, and then and only then have them dope, okay? And so right now our group has made these things, and we have a whole slew of them that are available for people to use. People think of these things as esoteric. We can make these things on, many gram scale, and I would just point out that when you're putting down monolayers or doping at a few percent, okay, when we can make them on 100 gram scale in my lab, that means that they're basically infinitely available. So finally, what I want to show you is that by understanding how to do chemistry, we can make compounds that are very clean dopants, that are extremely strong. They can dope things that with electron affinities as low as 2.2 eV, and they're air stable. You can handle them in air, like this pizza. Like this pizza, I will handle it in air, okay, but I would not store it for months in air, okay? But you can handle it, you can transfer it, okay? That we can tune their properties, we can tune the size, the shape of the dopants, and compared to other approaches to having air stable dopants, they're more reducing, they don't have side reactions. And so one of the holy grails for us was to be able to dope these materials for OLEDs, and we've shown that that works, and what we didn't expect was that they would stay doped for a period of hundreds of hours, if not years. Okay, so what I hope to show you today is that there are a variety of things that you can do, and that the materials that you can play with they're easy to play with. Okay, they're not going to go up in flames when you deal with them, and that you can modify the interfacial properties for doing a lot of different things, and you can modify conductivity. So with that, I will stop and thank you for listening, and if we have a minute for questions, I can take questions, or not, people can talk to me later.
Time for a couple questions.
Yeah.
So the slide where you're showing that you add for the light doping, heavy doping, same way you tell, versus the purification. Well, I'm still confused a little bit. I probably just missed it. If you kept, the curve was going downwards. So if I kept doping,
So
what happens if you dope too much?
What happens if you dope too much is you don't have a transistor. You start you start putting enough carriers in that you don't have it go off, and it just becomes conductive. So if you just put a few carriers in, it remains as a semiconductor. If you put a ton of carriers, we can heavily dope C60 and get conductivities up to 10 Siemens per centimeter. Okay, but that would be fine if we wanted to be, for example, an interlayer for extracting charge. But if you want to make it into a transistor, you just want to have just enough carriers to fill the trap levels.
So the follow-up question is, do you just have to do that by being really careful with the chemistry, in terms of molarity of the chemistry?
So this is done by vacuum deposition. Okay, you can do it. You can do solution things. So for example, we've worked with folks, Ted Sargent and Aram Amassian, and we're doing this now on perovskites, where you just put tiny, tiny, tiny amounts of dopant on, in the case of Sargent and Amassian, quantum dots, and you can passivate trap states. Okay, but if you start throwing tons of dopant in there, then you start really heavily doping the quantum dot. So what you need to do is basically do some empirical work to find out what concentration of dopant or how much dopant you need, and then if you have material of the same quality, okay, then you can go and you do that. And for Antoine Kahn, they can control that extremely precisely in their vacuum deposition chamber.
Any other questions? All right, let's thank Professor Marder one more
Thank
time.
you.